Hello everyone, today I'm just going to give you a short improvised tutorial intro into the CFD or CAD simulation tool I use, which is SolidWorks with the Flow Simulation plugin. Now this is far from a complete tutorial, but it's a short introduction. I will make more tutorial videos later on, and they will be a lot more detailed. This is just the complete process, very simplified with one example, so you have a brief idea of how I make these simulation videos. Of course, this example uses a specific software, which is SolidWorks, which is a payware, which is also used for professional simulation tools. But there is a student's version, which is relatively affordable on a yearly basis, and the fundamental principles also apply to other similar software, some of which is cheaper or free or different. This is just a general example and just to show you how it generally works. The next video like this that I will make will be more about the theory without actually using the software, just the theory of what is CAD, what is computer-aided design, how does 3D modeling work for engineering purposes, how do numerical simulations work, the mathematics behind what is numerics, why do we use it, how does it work, how do 3D models get saved for it, and so on. And after that, I would go into the details of each specific feature of this software or other similar softwares, and how to use each feature for specific purposes, how to simulate different types of vehicle or different types of situation, and what to keep in mind when using numerical simulation on different types of problem. But for now, I'll just do a very brief example. I might also talk about the other examples that I do videos on, and the concepts that I sometimes think up for fun, like the space plane that I do a few simulations on. But for now, let's start with the first basic example here, and I'll just draw this up and talk along with it, because this isn't a detailed tutorial, this is just basically an improvised trailer for a tutorial. So what we'll do today is something relatively simple, because I want this tutorial to include the simulation in real time, so the simulation shouldn't take too long. The whole thing shouldn't take too long, but at the same time I don't want it to be too rushed, so I'll use a relatively simple example. What we'll do today, as I've already named the file, you might see it, is an oblate lifting body, or a basic ellipsoid lifting body, re-entry body type thing at low speed gliding. So we start by drawing the first cross section, which is basically the back, and of course we can use these measures to introduce exact numbers to these sketches. So we say give the main cross section a wingspan of say 6 meters. Now this is all in millimeters, because that's how you usually work in engineering. In physics and the SI units are by standard meters, but the standard unit for engineering is millimeters, so 1/1000th of a meter. So really, in aerospace engineering, you might even come across the wingspan of a large airplane in millimeters. An airliner has a wingspan of 20,000 millimeters, not of 20 meters. Uh, then we give it a height of say 2,400 millimeters. So we got this kind of a flat ellipse. Now this isn't really a very specific concept like the other things I do, but this is just a very quick example. So the actual measures will probably not make too much sense, and it probably wouldn't fly too well either. We introduce a second plane. Now these are reference geometries, so they're not really part of the model yet. These are just the geometries we'll use to later create the actual 3D model. But let's give it a forward length of say 8 meters. Does that look okay? Because this is just a quick example, so really it's just about something that looks half decent, let's say 10 meters here. And we draw another cross section, and we'll draw 1/3 cross section, and then we can connect these cross sections together. Now we'll give this one different measures, of course, say a width of 2005, first typo of 2500, not 25,000, and a height or thickness of, I mean, this is looking alright, so let's just round it to 500. And then we can create a third third plane that is into the other direction, let's say 5000 millimeters. Obviously, usually when I come up with some concept for fun and I do all the calculations about it and then build a model and simulate it, uh, some 20 minutes of thinking and running calculations in my head go into every single one of these numbers I'm typing in. But again, this is just a quick example, so I'll just go with whatever looks remotely decent. We will make this one a lot closer to the center cross section, so we give it a width of say 5000 millimeters and a height of 1800. Now this is how basic CAD softwares usually work. Now there are many ways you can create shapes in them and import shapes from otherwhere and create all sorts of weird forms, but usually you start with very basic forms. You usually start by drawing up a sketch, or first of all you make a plane. You define a plane, which is a reference geometry. That's just a mathematical plane defined in space, and you can draw a 2D sketch on this plane from lines and splines and circles and half circles and rectangles and hexagons and whatever, and measure them out and connect them. And then you can create basic three-dimensional shapes based on these shapes and then apply further changes from them. There are a few other ways, but this is the standard way how you go. So the most normal way you start designing a part would be by making a sketch, and then you could say, for example, I want this sketch extruded 1000 millimeters, and then you get this kind of shape. But we don't want to do that. We want a somewhat continuous and curved form, so we use this feature. Now this is still in German. I'll probably set up my software in English language for later for more in-depth, more in-detail tutorials. But what we can do now is connect these three sketches, and we get a 3D shape that is curved between these sketches. And here we have the basic shape of our lifting body design that we're going to test today. That is probably not going to fly all too well, but it looks kind of nice actually. Now I'll show you a feature that is not directly sketch based, but is a modifier basically to the shape we already have, which is a Verrundung. It basically rounds edges, and it's very useful because actually you can round inner edges too, and thus create more material and make smooth, really smooth envelopes around several shapes that you're combining into each other, which is actually quite useful for basic aerodynamic design. But now we're just going to round this nose so it's not completely flat. And we get this kind of shape, which isn't really great, but for a first test, it's a start. It looks half decent. We're going to do the same with the back side, and now I'm going to add two fins so the simulation doesn't get too boring, which usually you would come up with proper wing profiles and do several mathematical planes, and then do the same thing we used to create this fuselage, to create several wing profiles connected to each other and thus create an airfoil. But the simpler way, just for a very rough estimate, for a very rough concept visualization, you can go a lot simpler. And this is a bit improvised now, so I don't have much time to think about what I'm doing because I'm talking at the same time. But I'm basically just going to draw up the onlooking outline of the airfoil onto a previously defined plane. Now this is an axis that I'm defining right now, which I'll then use to define another plane, and that I will then draw on. So we have these three planes that we start with. These are basically the three defining mathematically defined geometries that you start every other model with. And from there on, you can use mathematical definitions and numbers to define all other geometries that you're going to make. I think I'm not very much into artistic 3D modeling. I don't know much about that, but I can assume that there are differences from engineering 3D modeling, which is what I know about. I think one of the main differences is that here you can, of course, not define things, but if you're doing it somewhat well, you will clearly define every geometry with exact numbers rather than just draw something up. Now what I'm going to do is make a plane through this axis that is tilted towards the previously defined plane by, say, 20 degrees. And I'll use that plane to draw on, or I can even show a cross-section through that plane first, and then I'll draw two tail fins that make a sort of V-tail rudder structure. Now I'm going to draw on this plane, and I'm actually going to do exactly what I just said you shouldn't do, because it is just an example. I'm not going to use exactly defined numbers, but rather just draw something up that looks kind of acceptable. Let's see, are there any... let's just round these numbers so they make some form of sense. And now we can actually extrude that sketch to a width of, say, 50 millimeters. Now it's still a cross-section cut. If we turn that off, we have this fin, and now we're just going to round the edges of this fin a little bit so it isn't just a blunt surface. And of course, focusing too much on talking, you might make a few typos. The measures you use should, of course, be actual numbers and not some other form of sign on your keyboard. But we can round this so that it gives some form of aerodynamic airfoil rather than just a blunt surface. And we can then round the edges of this aerodynamic airfoil to be essentially buildable and not made of sharp edges, which is something you usually don't see in aviation, because the outside of an aircraft's fuselage, if you try to build a sharp edge on it, it usually doesn't stay sharp. So you usually want all edges to be somewhat rounded, be it with a very, very small radius. And now this is really the cool part about this feature, is that it works on inner edges like this one too. And you can imagine if I now drew a cube into this, I could use this on the inner edges and then on the outer edges, and I'd get this sort of enveloped inner cabin in this fuselage. But for now I'm just going to create this somewhat smoothly connected stabilizer fin, and now I'm going to mirror the basic structure, and being that I'm talking at the same time, I already did something slightly stupid, because usually you'd do that first and now apply all the roundings to both airfoils rather than one after another after you've already mirrored it. that was a bit dumb, but it's still gonna work. It's just gonna take a few seconds longer. And so we've got ourselves a first somewhat resemblance of a lifting body type vehicle that we can now run a basic aerodynamic simulation on. Now, one thing I should mention just about this software or CAD softwares in general, I will go more into detail about their use later on, but this is a part file, and there are two basic different sorts of file in a CAD software, which are part files and group or assembly files, and they're used to make basic mechanical assemblies. Now, there are some outlying ways to actually move parts in and of themselves, make them elastic or something, but usually parts are the building blocks you build, and this of course comes down to actual engineering. This of course is a simulation or resemblance of actual engineering or building processes, and the parts are single connected parts, while the assemblies are obviously assemblies of several parts which are stuck together and might then make a moving mechanism. Now, since I'm just drawing up the outlines of a fuselage, I've used a part file, but usually you would use many parts and assemble them together into an aircraft rather than build it in one part, obviously. And now we're going to make a simulation project, and it's already giving us a little alert here, which is that there's no inner volume, and this comes down to there being two basic types of aerodynamic or fluid dynamic simulation, really. This is a fluid simulation tool, so it can do aerodynamic simulation. It can also simulate the flow of water or oil or any other gas. And here are two main types of fluid simulation, which is internal and external. And internal would apply to things like tubing or cooling loops or such, where you have a hollow space within your model and water or air or whatever flows in that hollow space. And external is where you have a vehicle and you want to simulate the airflow around this. And once we change to external, this alert will no longer be a problem, because the problem we just had was that there's no hollow space within our part, and we don't need one if we're doing an external simulation. Then gravity can often be ignored in aerodynamics, but we can just turn it on, of course, with the standard constant, and we could use several components to make a vector towards any direction. So if we're flying upwards in a climb, or if we're kind of rolling sideways or something, we could adjust this vector, but for now I'll leave it just like that. Fluids, of course, is by standard water by default. We're gonna change that to air, because that's what the thing is supposed to fly in. We could, of course, simulate a submarine as well, then water would have been correct. Walls, we use standard walls. I'll add a little bit of roughness just to make it a somewhat real wall. And now we define our airflow also as a vector, and I'd say this thing is gliding downwards. Now these are just rough estimate numbers off the top of my head, since this isn't a real an actual project, but let's say it's flying at 100 meters per second, which of course, as you can see, this coordinate system down here, and what our vehicle looks like, the arrow is going to fly in negative z direction if it's flying forward, so minus 100. And let's say this is a lifting body, it's probably got quite a glide slope. Let's say the arrow meets it basically from below. Of course, this whole thing could be tilted, but the arrow relative to this thing's coordinate system hits from below, say at an angle of attack of some 15 degree maybe, or 12 degrees or something. Of course, you have to roughly approximate the trigonometric functions for this, because here you have two coordinates that add up to a vector and not an angle or direction, although there are ways to change this. You could do this in angles, but I'm not used to that way, so I usually use this one. We can add humidity to air, which usually doesn't cost too much computing power and actually kind of helps accelerate the solving of the computation. In which case we have to add a parameter as to how much humidity there is, and we can leave these the same. If we were flying at very high altitude, we would of course have to adjust the properties of the air, or if we want to fly in a very specific weather situation. But for now we'll just leave this at the standard that is set for sea level air conditions. And this is just, we've just changed this from an internal to an external study, so the space that is actually simulated has to be adjusted. And now we've got this nice space around our model that is being simulated. Now, of course, as real engineers, we're not going to leave that space just as the software defaulted it, but going to round those numbers so they make some sort of sense. So say 24 meters in every direction around it, and 40 meters ahead and behind it. Of course, in a real simulation, you'd actually set a much larger space just to make it more accurate, so that the turbulence caused by it has time to properly dissipate and re-affect it, rather than just leave the simulated space. But as a sort of amateur learning project, I'll leave it at this size to save computing power. And now we're going to what's basically the grid building tool, and this will make a lot more sense after I make my next video, where I'll explain the theory, the mathematics, and the basic principle of numerical simulation. But this is basically how precise we cut up that space. In order to simulate the aerodynamics in the space, we're going to cut it up into many little cubes, and these cubes are relatively simple to simulate. They just follow basic laws of aerodynamics, thermodynamics, and physics: conservation of mass, conservation of momentum, thermodynamic equation of air, and so on. And they're going to interact with each other, and in the beginning it's just going to be a starting state that doesn't make much sense, which is just completely uniform. The air is just in its starting condition everywhere and moving backwards. And then it's going to look for every piece where it doesn't make sense with the laws of physics and readjust this, and it's going to do that again and again, iterating and slowly converging towards an approximation of our laws of physics. Now, you can just leave this at standard, which is currently a net basically like this, but that's a bit inefficient. It's going to take a lot of computing power. As you can see, these are 70 by 70 by 140, roughly 700,000 cells, which is less than I usually use, but too much for a real-time demonstration. So I'm going to cut this down to some, say, 200,000 cells or even less. And of course, keep in mind that this isn't all. There will be further adjustments to that net, because as you can see down here, there are several ways that this can be made finer. So every single one of these cells can be divided up into more cells and more cells and more cells. And obviously we don't want to very accurately simulate some empty space here, but we do want to get a lot more detail on, say, the tail fins of this thing. So different cells will need a different level of detail. And what we're going to do here is say how many stages, how many powers of 2 will this be finer or more detailed under certain conditions. So first of all, when it actually touches this object, the boundary layer between this object and the area around it should be a lot more detailed. And I don't want to create too many cells, so I'll just look how much surface area does this have. That's about 180 square meters. So let's say we're going to make those parts finer by a factor of, wait again, by a factor of 8, so 3 powers of 2, and then we can add a few more things like channels, which is if the arrow is caught between two things, how many cells do you want for detail between these two things, and how much detail do you want on finer details of the geometry. And I think for our first demonstration this should be enough. We can try out, of course, how much computing power this is going to need by just starting one simulation and seeing how long it roughly takes. There's a few more adjustments we can make. We can say that it should stop after 2 travels, which is 2 times iterating completely back and forth. So any aerodynamic effect that starts goes all the way to the back 4 times, or say 2 times. That's a bit less accurate, but it's going to take half as long to compute. Then just for us to display, we'll set goals or readouts, which is values that we want to display during the simulation, so we can look at them and see the results. And I'll just take the aerodynamics forces working on this body, and now these will be displayed during the simulation, so we can see how much drag is it causing, how much lift is it causing. And now we can start our little oversimplified simulation. Save the project first maybe, and then click on starting, and maybe not use all my CPU cores, because I'm currently also recording this with a screen recording software, which also takes computing power, and I'm live streaming the ISS stream, so maybe not use all of my computer cores, just half of them, and eventually this window here pops up. And what it's currently doing is using the settings I've made for how I want to set up the grid, and looking at the geometry and setting up that grid. And now it's starting the actual simulation with all the previews that I have set up for the last simulations I've run. So if this is supposed to make sense, I'll have to reset those completely or set new previews. Now one thing we can see already is the I pause this for a moment so I can set this up and then watch it run. These are the forces working on it. You can see the coordinate system and these readouts. So this is basically lift and this is basically drag. Then we can already make cross-section previews, which I'll have to set up anew since this is a new model. For example, we can look at a certain plane. We can limit how much of it we want to see so it doesn't clutter our view too much. And which parameters, say pressure or speed, and now we can continue our study. Now this is running pretty fast right now because it only has very few cells. Usually when I actually run a simulation, it has some somewhere between 10 and 100 times as many cells, which doesn't proportionally affect the computing power needed, but a little bit more than proportionally, so it usually takes some 100 times as much computing power or time. We can set this up to also show us the cells we've made, and to be in a slightly higher resolution. And now we can watch it solve our simulation live. And currently it takes some 4 seconds per iteration. We've made 2 travels, 140 iteration, roughly, oh, now it's less than 10 minutes to solve this. Now, as the solver is running, you can see that over time, over iterations, it gets more and more accurate, and you can see this in these drag and lift readouts, which start making sense. This was excessively high in the beginning, then it kind of dipped down, then you had negative drag, which is of course impossible, but again, it starts off making no sense at all in the laws of physics, and it iterates and converges towards something that approximates our laws of physics. So in the beginning, it's just wrong, and it becomes more and more correct over time, and now these values do start making sense. You have a good bit of drag, which is roughly what you might estimate for this surface area and this speed, and lift, and a lift to drag ratio that makes sense for a lifting body, so it kind of makes sense now. Now you can read out different values as well, of course. You can also make the area that you actually display a bit smaller, so we get a bigger image on screen. And we can show temperature, for example. That's the air temperature. Of course, the air heats up as it rubs over this lifting body and heats up, and you can see the temperature distribution. And you can see quite well here that this is the standard grid, and it gets finer and finer and finer again as it approaches the surface of our fuselage. If I set the cross-section to be a little bit different, so maybe we can get a glimpse at the tail fins that we designed. These are a bit finer, so there's some really fine detail on them, and you can see the cells get smaller and smaller to encapsulate that detail. Of course, if you want to be really detailed, or if you simulate something more complicated, you might want to set up, you can set up a space that is unrelated to the geometry, where the cells just are finer to simulate something like wake turbulence or exhaust plumes exactly. Generally, there's a lot more features in the software. This is just a short preview that I'm making to give you a brief overview of how I make these simulations videos. In my next video, I'll just explain the theory and mathematics behind numerics and few things you might want to know about it, but then I'll go more into detail about specific features this software has and specific cases you can solve, like rotating parts for propellers and rotors, exhaust parts that you can use to simulate things like rocket engines, how to make an internal simulation, the difference between simulating air and water, the different features you have to create 3D models in the first place. And I might even go step away from aerodynamic simulation to show you things like structural analysis. Now this shows how these values are converging, which means that if they stay roughly the same, this indicates that the simulation is starting to make sense because it's not adjusting much over this value anymore. And indeed, it starts to stay more and more the same the more correct it gets. You can of course manually adjust the upper and lower boundary of these color schemes, so you can see a bit more detail in terms of how much pressure exactly is in a certain area, while the broader scale of course makes sense to see all of it and not just a one colored surface. Now, one interesting thing to keep in mind is that this is not the exact lift to drag ratio of the thing, because this isn't exactly the backwards coordinate. We've set it up so that the airflow is a vector and it does go upwards a little bit. So this is only the parasite drag of the aerodynamics we've made. The induced drag can be calculated with trigonometry and the direction of airflow, and this the lift actually induces a bit of drag since it is tilted backwards essentially towards the airstream. Now, one more parameter we can display, we can actually display quite a few different parameters, and this is just a brief overview. You can add more, but we can, for example, display turbulence. You can display turbulence, the energy in the turbulence, or the time for one rotation of turbulence, which gives you an idea of how turbulent the airflow is around a certain airfoil. Usually in the early phase of the simulation this gets underestimated a little bit though. You can display the humidity, that we've set the humidity for the surrounding air in the beginning, but of course as the air temperature changes around the fuselage, this value also changes, and that's how you get things like condensation clouds. We can show the air speed, the airflow in different directions in different components of the vector. And this is actually going pretty fast now. If I set this up to be a lot more detailed, like in the other simulation videos I make, then this entire simulation that is now going down in some 10 minutes usually takes around 1 day. I then put it to the background so I can do other things while this runs in the background. And that's why I usually don't show you the full process, but just the results, so it doesn't take 12 hours to show. Or usually more like 40 hours or something. The Falcon Heavy stage separation simulation I made, I think, took some 40 hours to render. Now this actually makes a surprising lot of sense, disappointingly, because I wanted to show you an example. These are the minimal and maximal values for certain values that these cells have, and often you can see very strange numbers here because this is a numeric approximation. It doesn't completely make sense, it just overall approximates making sense. So if you have a very detailed simulation, a single cell in that simulation might be some weird outlier and might not completely make sense because it's not simulated with enough detail. So, for example, if you have a ring and an airflow around that ring at, say, 100 meters per second, it makes sense that the maximum airspeed is some 120 meters per second, maybe on the upper side of the ring, because it flows faster than the average airflow around it there. But you can sometimes see a maximum airspeed value of some 5,000 meters per second when you're actually just simulating a small airplane with an airflow speed of 100 meters per second, and that's due to one tiny detail cell not making sense in the detail because it doesn't have enough detail. And the simulation is now finished, as you can see down here. We've done 2 travels as we've set up as our stopping condition, and now we can look at the results and for example, add these kinds of streamlines around the body, say 100 of them, and display speed on them. And ta-da, we can see, we can set up this to be a bit more resolved. And we can see the airspeed and airflow around our lifting body. And we can also look at cross sections that we can then let run through that model. Now this too is going a lot faster than usual because it's fewer cells, it takes less computing power. And that's how you get these nice cross sections of your aerodynamics. If we go back to the solver, that's this external window where we've seen the solving status and the preview, then we can see these setup goals of our simulation, and you can see not only the forces acting on them, but on the body, but also the torques, and thus you could now derive the center of drag or the center of pressure of the body and how aerodynamically stable or unstable it is given a certain center of gravity, and do a lot more interesting things, but again that would be more detailed. I've just given you a rough overview as to how these aerodynamic simulations work that I do. Now this video has already gotten a little bit long. Again, this is just an improvised little introduction to the tutorial series. The next video I'll make will be a lot shorter and more thought out and edited, and just be an explanation video about the theory of numerics, and then I'll start going into detail about every individual feature of this software, which will also be a lot shorter because it will just be one feature, not a complete simulation. So with this, I still hope this introduction into aerodynamic simulation was somewhat interesting to you, and as always, thanks for watching.